Hi, everybody. I'm Anca Dragan, and I wanted to share a little bit of an intro to experimental design with some principles to keep in mind as you're designing your experiment. So first, let's talk about what an experiment is in the first place. And to talk about that, I'll just mention that we think of experiments traditionally as being about people answering questions in medicine, for instance, about how people react to different treatments. And in robotics, we think of experimental design as mainly something that human-robot interaction researchers do when they set up user studies to test the design of robots that are to be used with and around humans. But there are lessons there that we can learn from them about designing experiments in robotics more broadly, even when your questions are algorithmic questions that are not directly about studying people. So even when we have sort of traditional problems like reinforcement learning, motion planning, et cetera, there are things that we should be thinking about when we're setting up our experiment. And so right off the bat, let me just say, these are the four ingredients we technically think about when it comes to experimental design. We talk about treatments. These are going to be the different conditions that you're testing. Responses, which are the measures. And then you're going to have experimental units, which if you're dealing with people, those would be your subjects, your participants, and then an allocation method, which is also called a subject allocation or an assignment method. So for very quickly, as a few examples, if you'd be in a medical field, a very traditional experiment would be your conditions, your treatments are the drug and the placebo. You are measuring certain symptom progression in the disease. Those are going to be your responses or your measures. Then your patients are going to be the subjects or the experimental units. And then the assignment method assigns subjects to the conditions. And typically that's done by what we call a between subject design in this area, where each patient will either be given the drug or the placebo, but not both. And the way we'll decide on that is by randomization. So remember that between subjects, it's a term that comes up. Now, in a human-robot interaction setting, an example might be, we can generate the robot's motion to be feasible only, do its thing, avoid bumping into things, etc. Or we can use an optimizer and optimize cost, optimize reward, something like that. And what we might be interested here as a question is, how does that affect how comfortable people are when they're working side by side with the robot? If you're energy efficient, for instance, you might have people end up being much more comfortable. So your subjects are the participants coming in, and the way you might allocate them might be between subjects, or you might choose something called within subjects, where each user will end up working with the robot both in the feasible condition and in the optimal condition, so that you can kind of get a comparison. So there are pros and cons between these two, and we'll touch upon that briefly later as well. Now, when you're in a robotics, kind of pure robotics, so to say, domain, by the way, I don't think there are pure robotics domains. I think everything's about people, but I'm biased. So if you have a question like, and I'm going to use here an example from when I wrote my first paper in robotics back in the day. So this was a question of, if I'm running a motion planner, a trajectory optimizer, I could do the traditional thing, which use a fixed goal configuration. Or I can account for the fact that there are many different ways to reach for an object, many different configurations that will work. And maybe it's useful for the optimizer to know about that set of goals. And so you might want to look at the effect that using a goal set has on the final cost of the solutions. And that's all well and good. Now, here's what's interesting. What are the experimental units when you don't have participants coming in? What's the equivalent of that? And so here what we have to think about is, what are going to be what are we going to measure the cost when we run these algorithms on? And the answer for experimental units here is the motion planning problem instances. They are the ones that are going to be looking at the two algorithms and evaluating them in a sense of, they're going to be able to tell you what the cost ended up being for each algorithm. So experimental units don't have to be subjects. They can be things like problem instances when you're doing algorithmic work. And you have to decide on what those are. And you have to decide on an allocation. Usually you just do within subjects here. Now, kind of stepping back, these are the ingredients of your experiment, but you don't just come up with them, in one shot and then that's it. You actually go through an iterative process if you want to do a good job. And that process starts with what your variables are. There are two main kinds of variables. There are a few more, but this is just a 15-minute crash course, so we're not going to go into that. There's dependent variables, which are essentially just going to be your measures. And then the more interesting part is, what are the independent variables? So the independent variables are not the same as the conditions or the treatments. The independent variables give rise to the conditions or treatments as you change, as you manipulate that independent variable. So for instance, what you actually change is the type of goal or the size of the goal set. That's your independent variable. And it gives rise to a treatment where the size is 1 and a treatment where the size is more, maybe things in between. So that's the actual variable you're changing. So it's not whether you're using algorithm 1 or algorithm 2. That's, technically that could be an independent variable, but it'd be a very cheating way to get at an independent variable. What you want to focus on, what you want to identify is what it is that is changing between these algorithms. And then you can form your hypothesis, which your hypothesis is going to have to look like an independent variable has a particular effect on a dependent variable. Or sometimes they're directional, like it positively affects or negatively affects the dependent variable. And so examples are optimizing motion will increase user comfort, or including goal sets in planning leads to lower cost solution. Notice it's not, I have an algorithm and it's better than the other one. It's the effect that an independent variable has, or maybe you can say a goal set size positively affects costs. And the reason I'm making a big deal out of this is because a lot of times when I look at robotics papers, they read something like this, right? There's going to be my algorithm, the other algorithm. I test mine, I test the other one, mine is better, end of story. And I think what's missing here a lot of the times is really sitting down and thinking, what is it that we're manipulating? What is the independent variable, set of independent variables? What are we changing here when we go from the other algorithm to my algorithm? And I think that's really important because forming a hypothesis in this way, by really thinking about what is the thing that you're changing, is going to force you to really articulate what your idea is, what your key insight is, right? So instead of just saying, I'm making a thing and it's better, you're going to come up with essentially the thing that's actually changing between the things, which is almost going to act as a more generalizable idea that's going to live beyond your application to one specific instance of an algorithm, and we're going to get back to that later. So good experiment design is going to really force you to sit back and reflect on, how could I articulate my idea? What is it that I'm proposing here? And then you're going to conduct an experiment. You're going to design an experiment to actually test that that thing that you're proposing is actually improving or seeing the effect that you're hypothesizing. So that brings us to this natural question, which is, how do you design a good experiment? How do you do this well? And the disclaimer here is, by the way, in my own work, I strayed away from my own advice that I'm going to give you here numerous times. I'm by no means perfect at this, but I do find it important for everyone to be aware of these issues and think about them and do, as best of a job as can be done. So taking a few steps back, let me first share this very basic thing about experiments, that they should ideally be controlled. You will have no problem doing that if you work with algorithms in the lab, but for more complex problems, the issues arise, and I want you to be aware of this. So when I say controlled, this has a very specific term in the experimental design literature. A controlled experiment is an experiment in which the experimenter is in charge of assigning experimental units to treatments. And that's to distinguish it from something called an observational study. So what's wrong with observational studies? Well, here's an example that I think is pretty indicative. So this is a famous example of an observational study gone wrong. And it goes back it's back in the day, and it was about studying the effects of estrogen treatment applied post-menopause to women, and looking at the effect on their health outcomes. So a team ran an observational study tracking over 90,000 women for 8 years. They recorded whether the women were taking estrogen or not, and they measured their coronary heart disease and a few other health indicators. And their analysis revealed that that low coronary heart disease, cardiovascular disease, correlates to estrogen treatment. So the conclusion was that estrogen treatment is good. People should take it post-menopause. It's going to help with their heart. But there's a problem here. And it has to do with the fact that it's not a controlled study. The experimenter did not assign the experimental units, the women here, to the two treatments, right? The two conditions. So instead, women decided whether they want to take estrogen or not. And that introduced what we call a confound. Basically, different women, if you're the kind of woman who wants to take estrogen to maybe improve your health, you're the kind of health conscious person who probably also is likely to exercise and do a lot of other things that are good for the health. And so the effect of that could not be disentangled from the effect that giving estrogen has. And in fact, when they ran a controlled study, it showed the opposite. Estrogen actually had a negative treatment, negative effect. And maybe it was something like health consciousness that has such a positive effect that compensated for that. And it made it seem like the estrogen was helping. So this idea of confounds is really foundational to good experiment design. And this is the main thing you want to watch out for. You want to identify those independent variables, and you want to test your hypothesis by avoiding confounds. And running a controlled study and a controlled experiment is, the first step towards that. Now, what's a confound in general? A confounding variable is a variable whose effect cannot be distinguished from the effect of your independent variable or variables. So health consciousness in the observational study is a confound, right? Because from the data, we cannot distinguish whether the improvement in health outcomes came from the treatment or from, these other things that people are doing because they were health conscious. So in user studies, we might worry, for instance, about properties of the population that is getting these treatments. So we might end up with a confound that's experience with robots. If in one condition we end up with a set of participants that are have much higher exposure to robots, and therefore they're more comfortable around it, that's going to affect the data. So that's going to be a confound. If we use a within subject design, then so by the way, experience with robots, this is the kind of thing that you can eliminate as a confound, even without identifying that it could be a confound, because you can make sure to randomize and have enough people and randomize. So that's a thing, and not quite the kind of problem that you're going to have to worry about when your population is really, motion planning problems, for instance. With user studies, though, we also worry about ordering effects. If we're doing within subject designs where people are doing the task in one condition and again in the other condition, then we might see them improve at the task, not because of what the robot is doing, but really because of they've gotten better at it. And we fix that by something called counterbalancing. So we make sure that we have half the participants in one order, the other half of the participants in the other order, and the generalization of that for more conditions. Okay, so experience with robots, ordering effects. Now, some confounds are not about the population. They're about differences between the methods you're testing that are not your independent variables. So they're extraneous differences. So for instance, in a test about feasible versus optimal motion, I might not be consistent in where I time the trajectories that get executed on the robot. And if optimal motion ends up kind of having slower motion, that might lead people to be comfortable because of that timing difference and not because of the inherent difference between the way that these motions were, the geometry was generated. And so that's the kind of thing that you have to think about ahead of time and control for explicitly. And you want to write in your paper that you thought about it and this is the way you've controlled for it. So that's an example. Trajectory timing. There's also differences that creep in that are very, very common. And these happen regardless of whether you're dealing with people or not. So for instance, you're going to end up with algorithmic hyperparameters. So when you tune your hyperparameters, this might be obvious, but still some people don't do it. So when you tune your hyperparameters for your algorithm, but you don't for the baseline, then you've introduced a confound because you don't know whether the improvement you're seeing was just because of that tuning. And so it's not even enough to use the same hyperparameters, because if you use the same hyperparameters, but you tuned them, that set, to be based on your algorithm performing well, then all of a sudden you still have a confound. And so you really want to ideally pick validation data and tune basically optimize the baseline and your algorithm separately, and do whatever, give each algorithm the best shot you can give it. So that's kind of a common thing. You might be able to also blind yourself to which algorithm you're tuning if they happen to have the same hyperparameters, so that you don't invest a lot of work and careful finessing and tuning of one. That your mileage might vary with that. It's really not very easy to do in a lot of situations. Okay, so another example is differences between algorithms that slip in that are not captured by independent variables. So coming back to this picture, your idea might be a way to improve the state representation. And you might say, oh my God, I improved the state representation. This is great. It really improves the dependent measure. But what if, for whatever reason, this method that you were testing was a second order method, whereas the baseline that was using the old state representation was also a first order method? Well, you've introduced a confound with that. And this might happen more often than you might think, because, for instance, it might be that there's something about that new state representation that gels particularly well with the second order method. Or more often than not, it happens because we come up with an algorithm and the state of the art is not just that one change away from our algorithm, it's 2 or 3 or even more changes away. And then if we close our eyes to these changes, then we run the risk of attributing the improvement to the wrong reason, and then science goes down the drain. Or if another thing we can do is we don't identify the reason, we just say, look, this algorithm is better than this other one, trust me, this experiment says so. And again, we kind of lose touch with science, because without understanding the why, we're not really providing a lot of insight into the problem. So, and it's hard to generalize that to other algorithms. So I think it's really important to identify the independent variables correctly. And the way we can think about this is by what we call a factorial design. So you're going to have your state of the art, and instead of just testing your state of the algorithm, which is a new state representation and the second order method, you're going to break it up into 2 independent variables, state representation being one, optimizer being the other one. And you're going to test the full 2x2 factorial here. And this is helpful because what might be happening underneath the hood is you might notice that you might find an advantage of this combined method relative to the state of the art. But underneath the hood, what might be happening is that this is really an advantage that comes from the second order aspect and not from the new state representation. And it could even be that your new state representation does not help at all. In fact, it could be that it actually hinders, but then the second order more than compensates for that. So you have to essentially be very careful about these factorials so that you don't end up accidentally deceiving the reader with your message. And now, as you get more independent variables, you end up with, the full factorials really blow up. And in those cases, you should either kind of take a step back and make sure that you really think all those independent variables are necessary, or at the very least make an informed decision about which cells of this full factorial you want to leave out and explain that to your reader. Okay, so besides avoiding confounds, an important property of an experiment is construct validity, which means that what you're measuring is actually what you want to measure. And this breaks all the time when we take IQ tests and we think of them as measures of intelligence, when we ask people to rate their comfort and we think of that as being the actual comfort that they're experiencing. When we use sum squared error on test data and we think of that as accuracy, but and we're not accounting for the fact that different types of mistakes actually cost differently, and you know, we really need a much more nuanced measure there. Or when we look at the final solution of that comes out of the final cost that comes out of an optimizer without necessarily thinking about, you know, timing aspects and stuff like that. So another concept is external validity, which is really important. You want your conclusions to be generalizable, and so you have to set up your experiment to allow for that. And conversely, you want to only claim the scope that you're actually generalizing to, that's actually backed up by your experiment. So to do that, you want to make sure that your experimental units are sampled from the target population. Like, don't run a study on a 25-year-old wild male when you want to claim something about the general population. And remember, the experimental units in algorithmic settings are the problem instances. And so what you want to make sure is that they're representative of the kinds of problems that you want to say that change actually is helpful. So I kick myself every time I test something on a random MVP or on a randomly generated world, because real worlds will look different and I lose that external validity. So increasing generalizability means covering many types of experimental units. It also means something more subtle, which is, remember how we were talking about goal sets versus a fixed goal in my first paper? Well, in my paper, I manipulated that via two algorithms, right? I chose CHOMP, which was a baseline, and I added goal sets and it became goal set CHOMP. And my generalization was basically there. Like, that was it. It was, you know, goal sets help CHOMP. So I wish that I would have thought about actually applying this to different algorithms, to different optimizers, because the inside was actually much more general than the specific of CHOMP. So instead of ending up with, you know, a new and improved version of CHOMP, which is now out of date, we could have come up with something that was, you know, really goal sets. They're helpful whenever you have an optimization-based motion planner. And we could have gotten at that by really testing on a wide range of such optimizers, which is harder to do, but nonetheless. Okay, so these are the ingredients of an experiment. The key is really to figure out what your independent variables are and to make sure you can test your hypothesized effect of these independent variables cleanly, without confounds, and with an eye towards construct and external validity. And again, remember, formulating hypotheses in terms of independent variables will force you to clearly articulate your key idea, and then good experiment design enables you to actually test that idea. With that, thank you.